We'll start recording. How was your exam? CMTF question was easy. Did you face any problems in the exams for this course? No answers. How was your exam, CMTF exam? It went okay or
Good,
bad or good or?
Good, sir. Good, sir.
That's what I have. Okay. I have just received the answer script, right? What means just 1 day ago. So I have not yet checked your answer scripts. Generally, for offline exam, we receive the answer scripts after the exam itself, and generally I check it and show it to you in one week. But this time, let us see, because it will take more time to check, and we have to see also what is the modality of answer scripts. So what I'm going to do is quickly just gloss over through the questions once for the mid-sem exam, and then we will go back to. And when we are discussing about the answer scripts later on, then again we can come back to this. Okay. I hope you can still hear me. If you cannot hear
Yes, sir. Yes,
me, please let me know. Can you hear me? Students, hello.
Yes, sir. Yes, sir. Yes, sir.
Okay, I wrongly pressed the aeroplane mode, so it got disconnected in between. In general, also internet connection has been very poor, so just let me know whenever there is issue. So let us quickly gloss over through these questions. Okay. So if you have any questions, you can ask me, because otherwise I don't know that whether I am connected or not. So if some feedback is there, that is easy for me. So first question was, give one example each. So most of the questions are from standard whatever we have discussed in the class, except the problem. So give one example each for second order PD and for second order parabolic PD and for second order hyperbolic PD, and show the domain of influence and domain of dependence for each of these two types of equations, and with two independent variables. Okay. So this we have discussed in the class. You can give other examples also. So one example we have discussed in the class. Parabolic PD is the 1D transient diffusion equation, and second order hyperbolic PD is the wave equation. Okay. So you can give these two examples or any other examples that you could thought of, and then you have to show the domain of influence and domain of dependence. That also we have discussed in the class, I think, how the domain of influence and domain of dependence looks like. So this is for the parabolic PD. You can show the domain of influence, and the domain of dependence is the bottom part below P point. Similarly, for the hyperbolic PD, we have discussed. So domain of influence is this region. Domain of dependence is the other region below this. Okay, from which can affect the values at point P. Then the second question. So this is very standard. Second question was, give an example of a situation where when the energy conservation equation becomes the first order PD and is hyperbolic in nature. Why does this happen? Derive the equation for characteristic of this PD. show the domain of influence and domain of dependence. Okay, this also we have discussed. What is an example of a situation where the energy conservation equation becomes a first order PD and is hyperbolic in nature? When the
Sir,
diffusion term is
this
negligible, diffusion term goes to zero. Okay.
So,
Yes, when the diffusion term goes to zero. So that we have discussed. I think it is here. What is this content preparation every time it is coming? This case, okay. Diffusion term is zero. So once the diffusion term goes to zero, the nature of the characteristic changes. Okay. So as a result, uh, because the diffusion term it goes to it changes parabolic nature to its hyperbolic nature. Okay, to the hyperbolic nature. And equation of characteristics also we have derived here. Sorry, reflexes are not working. Equation of characteristics we have derived here. Oh, not this one. Sorry. This is the equation of the characteristic, and this is the characteristic line, and the domain of influence and domain of is not the entire line, it's just a single point. Okay, which is given by the at a distance of u infinity into t. Okay. So it can only influence the point, any point p here can only influence a point which is u infinity into t away, not the entire region. Similarly, it can only influence, it can only be influenced by any which is u infinity by t away in the other direction. This physically also we have understood previously. Let's say some flow is okay, and a disturbance is moving through the flow, and there is no diffusion. So only because of the flow the disturbance. So if there is any disturbance at time t equal to 0 somewhere, it will be at a position of u infinity into delta t after time delta t. Okay, and u infinity into 2 delta t after time 2 delta t. So always it is at a position of u infinity into t, where t is the time. So this can only influence a single point, okay, at a particular time. So the characteristic is the domain of dependence and domain of influences are a single points, okay, not the line. So that is also important. The governing equation, I have given a lot of marks because some of you were asking that time is short in online exams. So as a result, actually this is should be a 8 marks question, but I have given 12 marks for this. The governing equation for the 2D potential flow for a compressible fluid flow over thin. This also we have discussed. Okay, 1 minus m
sir,
infinity square del square phi
sir,
del x square. So del square phi del.
sir,
Tell me.
sir, about
Tell
question two,
me.
sir, about question two, the region should be confined along the line, no, sir.
It is confined along the line. It is confined along the line, but the
But
influence is only
several points.
at a single. The point is along the line.
Oh, the point
Okay,
is along the
but
line.
the
Okay, at
location of
several
the
points.
point along the line depends on not several points. It's only a single point for a particular time, which is at a distance of u infinity t. Okay, along the x direction. So if I go back to this image, you know the line of the characteristic line, this one.
Yes, sir. Yes, sir.
So say this is the point. Okay, I hope you can see my mouse cursor.
No, sir.
Okay, this is
Lagging.
the point at which okay, there is lag. Okay, so I'm showing putting my mouse cursor over the red line at one of the cross sections, green
Yes,
cross
sir. No,
sections. Okay,
no visible, sir.
so say this is the point P, means this is the current point, current state. So it can only, yes, it can only influence. So it can influence the value. That is correct. it can influence the value along the entire line. Okay, at any particular time, it will influence a single point, but that is to what you are saying. It can influence along the
Sir,
entire
if I am taking
line.
delta t
It is restricted to
small,
a line.
sir, if I
Yes.
am taking
No, no.
delta t is
Yes.
small time interval, then it will for different time it will give several points of affectance, no sir?
Correct, correct. No, no, no. Your point is correct. I misunderstood. Your point is correct. So all the points are located along the line, but it can be anywhere along the line. That is correct. Okay. So instead of this type of thing, where it is a region between two lines, okay, and along the line it changes, this region changes. Here it is always restricted, means the two lines have collapsed into a single line. It is always restricted to a single line. Your point is correct. It is along the line. Okay, this is along the line, and the domain of dependence also is along the line. These are several points along the line. Correct. Point is correct. Clear? Is it clear to you? Who had asked this question? Is my voice breaking off? Can anyone respond whether I am audible?
Yes, sir, you are
I'm
audible.
confused.
Yes, sir, you are audible.
Okay.
Yes, sir, you are. Yes,
Okay.
sir, you are audible now.
Was my point? Was my point clear?
Hello.
Was my point clear?
Yes, sir.
Okay. So then point 3 also we have discussed, question 3 we have discussed in the class, and so the nature of characteristics will depend on the value m infinity. We have seen three cases. For m infinity means for Mach number lower than 1, it is elliptic in nature, higher than 1, hyperbolic in nature, and equal to 1, parabolic in nature. So this also is a very standard problem. So you have to show that it depends on the m infinity value. Derive a finite difference approximation of mixed derivatives. This also is discussed in the, okay. So I think this is the the standard discussed. I am not going through it. Is there in your notes how to finite difference approximation of del square phi? I think every time. What is this content processing? Mixed derivative term. Okay, like this we get derived. So final one was a problem where you have to consider a 1D bar, okay, thin bar of length 4.4 meter, cross sectional area 1 centimeter, thermal conductivity 100 watt per meter Kelvin. The bar is subjected, bar or rod, okay, it's like a long bar, thin long bar. Bar is subjected to uniform heat generation at the rate of 10 to the power 6 watt per meter cube. Two ends of the bar are kept at two temperatures, 0 degree and 100 degree centigrade. And it is mentioned that temperature gradients are significant only along the length of the bar. It means that it is a 1D problem. Means along the cross section there is no variation. So like a single line is there one side. So it is somewhat similar to this problem. Okay, it is similar to this problem.
So my independent variable in that case only x, not t time, sir. No?
Independent variable will be only x because it's, I think it's a steady state problem. Yes, it's only x.
Sir,
okay.
Sir, that the flax parts are only, sir. Sir, I have a problem, sir.
I will come to that. So T is equal to TA and T equal to TB, similar type of arrangement. Single line, and instead of transient, this is a steady state conduction problem, but with a source term. Okay. Source term is given as 10 to the power 6 watt per meter cube. So using FD method, finite difference method, formulate the discretized equations and determine the steady state temperature distribution along the bar. Steady state temperature distribution. Okay. So you don't need any initial condition. What is the heat flux at the center of the bar? For the finite difference formulation, divide the bar into 3 internal grid points and 2 boundary grid points. Okay. Very standard problem. So you can just take a domain like this. Let me just check. Okay, you can take a domain like this. So you have this. So 1 point, I think 3 internal grid points are given, right? Let me check. 3 internal and 2
Yes,
boundary
sir.
grid
Yes, sir.
points.
Yes, sir.
Okay, so it's a very simple problem. If it was more grid points, your calculations will be longer because you say time is short. On the online exam, I have given very less, very short problem. Okay. So equidistance. My drawing is not equidistant, but let's say it is equidistance. All the points are equidistance from each other, and these points are 2, 3, 4, and 5. Okay. So we have to find the temperature distribution at 2, 3, and 4 because T1 is given. T1 is I think 0 degrees centigrade or something like, and T5 is 100 degrees centigrade. Okay, is it like this? Yes. So it's just you discretize the 1D conduction steady state conduction equation, d square T dx square plus s is equal to 0 using finite difference approximation. And you will get, so you have to do this for each of the internal grid points for 0.2 or 0.3 and for 0.4. So you will get 3 equations. Okay. So 0.2 equation will also have the term T1 and T3. 0.3 equation will also have the term T2 and T4. And 0.4 equation will also have the term T3 and T5. Okay. So 3 equations and 3 unknowns. T2, T3, T4. T1 and T5 unknown. Based on this, you can easily find out the temperature. I don't have the answer right now.
I can find 3
Yes,
first
tell me.
and then 1.
Voice is not clear.
I can
Can you repeat?
I can find 3 first and then 2 or 4 also, no, sir?
Yes, yes. There is no like it's not moving in any direction. Okay, you have 3 equations, 3 unknowns. Independently, you cannot find 3, right? Because T2
Yes,
and
yes, sir.
T4 are. So
Yes, sir.
ultimately, you have to solve these 3 equations together for the 3 unknowns and find the values. So in which way you eliminate, that is fine. Means I can eliminate T2 and T4 to get T3, or I can eliminate T4 and T3 to get T2. Ultimately, you have to get the 3 temperature values by solving 3 means 3 equations, 3 unknowns. So it's not difficult. It's just a method of elimination you can use, and actually it's a very easy problem. I have given a lot of marks because of online exam, and the heat flux at the center you can calculate in any way. The accurate way is if you take a central difference, so T4 minus T2 by this distance. Okay, so this is dt dx. Heat flux at the center is minus k dt dx, right? At the center, so at point 3. Okay, this one. So I can just write it as minus k T4 minus T2 by what is that? If each of these grid is delta x, so you can easily calculate what is delta x. So this will be 2 delta x. Okay, this will be the heat flux. So I don't have the exact answer values. We will discuss when I can show the copies. But I don't know how to show the copies in online mode. Means whether we are supposed to give you the on soft copies or what to be done. So let us come back to our discussion. Any questions regarding? So I am expecting that most of you will perform very well in the midterm. So your projects will become very important in that case. The project has 25% marks and it will become very important. Uh, so for the grading part also. Keep that in mind and we will discuss this later on. What can be the projects, typical projects. So we have discussed the basics of finite difference, and you should be in a position right now to solve any typical problem involving finite difference. Means ultimately any typical problem, CFD problem, will have some differential, and any of these differentiation terms you how to tackle using finite difference approximation, whether it's a first order term, second order mixed term, any of the derivatives you can just change into some finite difference approximation and you will get a algebraic equation. Now depending on how many grid points you have, you will get that number of equations and unknowns, and you can solve those equations to get the solution. If it's an unsteady problem, you will also get a matching type of solution. So any of the problems you should be able to solve for finite difference approximation. It's not difficult. The concept is very simple, and that's why it is very advantageous to use finite difference approach or even very complicated physics, where the physics is very complex. Means there are multiple terms and the terms are quite complex. Because you know how to tackle each term quickly, you can get finite difference approximation for the complex equation also. But there are limitations of the finite difference. Okay, one limitation is that you need to divide the domain into a very structured type of grid. Okay, means say you have a 2D domain, very arbitrary domain like this. Okay, you cannot divide the domain into this type of control volume. So you have to into some square type of control volumes. Okay, so say straight lines, you divide it into straight lines along each of this x-axis and y, and then you can use finite difference approximations. But what will happen to the boundaries? Then you have to assume that something like you can assume that the domain is total domain is larger. For example, again, if I go back to the drawing board, yeah, not this one, sorry. Okay, so you have to assume that, say, if you have a very arbitrary domain in finite difference, so finite difference advantage is that you can tackle complex physics and it is very easy. But say you have a very arbitrary domain like this, then what you have to do is you have to take a regular domain around this, okay, or some regular type of domain, and then I can avoid it. What is this? Divide it into straight lines like this. Okay, so all the control volumes are still similar in nature. Means rectangular type. So like this you have to divide, and now what you have to do is you have to formulate the equations so that the equations also take into account the boundary effects. For example, if you are solving a conductive and you have boundary conditions here, some adiabatic condition, you can assume that these grid points which are outside the domain have zero thermal conductivity, okay, or very small, like negligible thermal conductivity, so that although they are solved during the problem solution of the problem, they do not influence the temperature field because they have zero thermal conductivity. No heat can go out this wall. Okay. Another thing, then you will have to assume either the grid point is inside the wall, means control volume, or outside the wall. Means you cannot resolve properly the grid point, so your boundary will look something like this, jagged, staircase like. Okay, because you are unable to accurately capture this. So there are other ways to tackle these things, but I am saying from a simple point of view. Okay, so your boundary will actually, so you have to take very fine mesh, otherwise your boundary will look like this, means something like this. Means it will be like a staircase kind of. So these are some of the drawbacks. Okay. So now we will discuss the other method, which is the most widely used method, which is known as the finite volume method, and The rest of the course is focused on finite volume method. Okay, the entire and all this most of this software and other course generally typically written for project and everything are based on finite volume method because it is very versatile in nature and it has a lot of advantages. Okay. For very simple course, we still use finite difference method when say you are trying to solve a assignment problem or a simple project where you need to write a quick code. Then finite difference method, but for large scale problems, typically nowadays we use finite. So what is the difference between finite volume and finite difference? Actually, the difference is not too much. Means uh, actually there is a lot of difference, but for simple problems the difference is not very apparent. Let me first describe what is finite volume method. Okay, you must already know, those who have taken the course with me already know this part is exactly similar to what we have discussed in the elective course. Syllabus is same, but those who are new to CFD, for them I am just stressing this. So this actually uses the integral form of the conservation equations. Okay, conservation equations like say energy equation or momentum equation can be described in differential form like we have seen previously or in integral form. Okay, actually here also we start with the differential form, but we integrate over the entire domain. Okay, or control volumes, each control volume. So what we do, I will come to an example later. Just let me go through these points first. We divide the domain into a finite number of control volumes. Okay, say there is a domain like this, arbitrary domain like this. The domain is divided into smaller volumes. Okay, these volumes are known as control volumes. Okay, so each of the subdomain, which is given by this blue, is a control volume. They can be arbitrary in shape, they can be regular in shape, they can be triangular, like they can be say rectangular or say any other type of quadrilateral or pentagonal, hexagonal, whatever. Okay, no limitation on the number of sides. Only thing is that we are dividing this domain into a finite number of control volumes, not infinite. Means these control volumes are not infinitesimal in size. Okay, they have a finite volume. They are not infinitesimal in size. They have a finite volume. Okay, if they are infinitesimal in size, so they will become like a point, and the differential forms of the equations are valid for the point. But once we have this as a volume, we have to convert this equation, differential equation, so that it gives the conservation over the entire domain. I will come to this later to this point, but the conservation over the entire volume, each of these volumes. Okay, by integrating the differential equation for that control volume, and we will see how to do that. That's why this name has come, finite volume method. Okay, finite number of control volumes of finite size. Typically, each control volume is also represented by a single grid point, which some people may call as node, but generally we in CFD language we call grid point if for FVM, finite volume based method. For FEM based methods, these are typically called as nodes, and the control volumes are typically called as elements. Okay, so elements and nodes are generally used for finite element type of method, and for finite volume type of method, we generally call this as control volume and grid point. Okay, the grid points can be at the center of the control volume, or they may not be at the our formulation. Typically, the centroid means what is the center point. Okay, and the properties, any of the properties, scalar quantities like temperature, pressure, density. Okay, these are defined at these grid points and only at the grid points. Okay, so for example, for this control volume, there is only a single value of temperature which is defined at the grid points. So if I say what is the temperature at this point, at some other point in the control volume, we cannot say. You have to assume that the grid point temperature is valid over the entire control volume. So the entire control volume is like a single unit, minimum pixel, and you cannot resolve within the control volume what is the temperature or pressure or density. So ultimately, depending on the number of control volumes, your resolution of the solution will depend on that. If I divide a domain into 100 control volumes, you will get 100 temperatures. Okay, you have to plot the 100 temperatures. If I divide it into 10,000 control volumes, you will get 10,000 temperatures. So your solution will look smoother in the. Okay. So these are some of the typical points. Now you might be confused, right? What is the exact difference? What do we mean by dividing into finite number of control volumes? So let me just go. We'll go through the steps once, but let us take a simple example. A very simple example. Again, we will go back to with source. So always we take this type of equation because this is a standard example which can be adapted for any problem like thermal conductivity type of problem, or it's a species reaction type of problem, or even for the convection problem, when you have say the viscous terms and the source terms can be tackled in this way. Okay, so this is like a small part of a generally. Yes, tell me.
Sir, sir, you told that if we divide our domain in 1,000 control volume, then we will get 1,000 grid point, na, which will be at center of each control volume.
Yes.
So you tell that the properties we are measuring temperature or density
Temperature, pressure. Yes.
at grid point will be sir
Yes.
equal for all the points in that control volume, sir.
No. I think you are confused. All the points in control volume does not make sense, right? If you each control volume has a single grid point. Means say this is the, you can see here, right? This is our geometry, entire domain. So how many control volumes you have? Around 10, 15. I don't
Yes, sir.
know, but maybe 15 control volumes are there. Each is represented by a single grid point, not multiple grid points. Single grid point at its centroid. Typically at its centroid. Need not be at the centroid, but for our course, let us assume that it is at the centroid. So if there are 15 control volumes, there are 15 grid points, and properties are represented at these 15 points. Okay. If you have 1,000 control volumes, you will have 1,000 grid points. For each control volume, 1 point. But because the control, if you divide it into 1,000 control volumes, what will be the size of the control volumes? It will be much, because they are dividing into large number of control volumes, and the total domain size is fixed. Each of the control volume will be very small in size. So what will happen? The accuracy will improve. Okay.
We
Means
will get
because you have very small control volumes, uniform means smoother distribution. You cannot see uniform or not, depending on the boundary condition profile. Okay, you will get more accurate. Means you will be able to resolve more. It's like so you are watching a movie at 480p or 360p resolution, and the same movie you are or YouTube video, same YouTube video you are watching at 1080p resolution. Okay, it's a similar type of thing. So 360p, you are dividing the domain into 360 vertical pixels, and accordingly you can scale the number of horizontal pixels. And for 1080p, you are dividing the domain into 1080 vertical pixels. Means 1080 vertical control volumes, you can say, for the 1080p video. And similarly, along the horizontal, you have 1920 grid points for the video. So your ultimate resolution is 1080 into 1920. Similarly, if you keep on increasing, if you go to 4K video, you will have more number of points, but the size of each point is smaller. So as a result, when you look at it from the overall perspective, your solution looks much more resolved, much more smoother. Right? That is the same thing. So a 144p video and a 1080p video, you can see what is the difference. Huge difference is there. Even 360p also, if you look at it. Same thing also here. Okay, resolution is better, but you will obviously need more memory to solve. More time will be required for solving because number of equations are larger. Number of equations, you remember, depend on the points that we will see later. It is equal to the number of points. So obviously those will also increase. So there is a trade-off, and accordingly we decide what is the number of control volume. Say we have very limited resource. This time what has happened? All the second year students are facing huge difficulty in their projects because they are using their laptops at home to run this, and as a result, and they have to do some realistic problem, right? For example, for my students, they are solving either energy storage systems problems or some problem related to say melting and solidification. So again, with flow, melting solidification with flow in a complex geometry. Okay, so in those cases, if you want to resolve the domain properly, you need large number of control volumes. But say if I take 1 million control volumes, then the solution may take 1 month to run in a laptop, which is not feasible at all. If I had access to a very high-end server, it might be possible to run it in 1 week. And if it was say something like a supercomputer and the code is parallelized, it may even be fast. But because that limitation is there, now they have to do with a much coarser grid. Instead of 1 million grid, they may be taking only 10,000 control volumes and 10,000 grid points. Okay, so what will happen is this that their results will look coarse, but it will be still be physically correct. The results will not look good, but it will be still be physical, but it will not give rise to smooth solution. Is it clear? Is my point clear?
So, sir, for each control volume, we have only one grid point for which we have to find the values of properties.
Correct. Correct.
Yes, sir. Okay, sir.
Let us see one. Today I have some time. So, I agree. I remove the cases or what? Let me check. Let me check. Just one. I will show you how what artist looks like. None of this has equation. This one will be fine. This is from a realistic problem that we are tackling for one of the projects on energy storage, writing our own code. So what we mean by pixel and all this will be clear. So let us, it will take some time to load. We come back to our discussion here. So let us consider the 1D diffusion with source term. ddx of gamma d phi dx plus s equal to 0. Phi is the variable, dependent variable. It can be temperature, it can be velocity, or like it can be chemical what is it, concentration. Okay, accordingly gamma may be thermal conductivity, viscosity, or diffusivity, mass diffusivity. Okay, it is loaded. Let me show you. So this domain is divided into grids like this. Okay, what you can look, rectangle, square grids like this. Okay, and certain regions are there where we have some material which we call as phase change material, which can absorb heat and can melt. And outside the phase change material, there is flow occurring. Okay, flow may not be very clear right now. So so flow is coming from the left hand side, going out of the right hand, and this flow is bringing in high temperature fluid like this. Okay, with time it is bringing in high temperature fluid like this. Initially the entire domain brings in high temperature fluid, and As a result of this high temperature fluid, the phase change material which is contained in some spheres start melting, and ultimately the full melting occurs. Okay. So, and the melt fraction is shown like this. So initially no melting is there. With the time, melting is occurring, and gradually first row melts faster because hot temperature is there. Then second row will melt, third row will melt. So what you can see here, okay, I will zoom in one of these. Okay. See this boundary, it is zigzagging in pattern, right? So what has happened is that because of limitation, we are taking somewhat coarser grid. Okay. So if we could have taken a finer grid, still zigzag pattern will be there, but the zigzag pattern will be much smoother, right, as compared to this. We can always interpolate to remove the zigzag pattern also. The actual so each of the squares that you see here, I will again zoom in more. Okay. Oh, okay. Now this is better. Each of these square is a control volume in our simulation, and each of them are represented by a single point at its center. Okay. So the center value for this point, if I put the center value of temperature will be some temperature at this point. Okay. And the center value of temperature at this point is some other temperature. Center value of temperature at this point. Let us go back to some initial. Okay, actually take plot interpolates. That's why you get you will not be able to understand. Let me go to this plot only. This is better. So this is known as something called liquid fraction. How much liquid is there? So here liquid fraction is 1, means fully liquid. Here liquid is 0. And in between you see some center value is there, means it may be 0.5 or 0.3 or 0.2. Okay. So you cannot resolve the variation within the volumes. Okay. What variation you are seeing in the volumes here is what the software, means take plot, plotting, interpolating by itself. Okay. Actually it is just a sharp interface like this. Actually our results are not actually distributed like this. Okay. So our results look like this only. So we have a value 1 here. It may be very high, 0.8 or something here. It may be 0.5 here. It may be 0.1 here. 0.7. So based on this value, take plot is combining this to draw some lines. But the value is a single value at each of this control volume. You do not have separate values. And the value is given at the center point. So although the line is shown here, actually we have just a value at the center point. Okay, that is the important thing. And if you have more pixels, your value. So if I divide this into 10 more pixels in each direction, means 10 more control volumes, obviously you will get a much smoother solution. It will not, this staircase type of effect will decrease significantly. You will get a more rounded solution. This is supposed to be a circle. So you are supposed to get a rounded solution. But because of coarser resolution, what is happening? You are not getting a circle. You are getting this type of solution. There are other ways to smoothen it out, but this is the intrinsically this is the problem. Okay, with coarser mesh. But the problem is still physically correct. It is that it is less accurate at the boundary. So if you want to calculate terms like heat flux at the boundary of this, so your heat flux calculation will be more inaccurate. Means there will be more error because you are approximating this in a crude way at the boundary. Okay? So this is what I mean. Come back. Let us come back to this. So now instead of directly discretizing this, like we do in finite difference equation, our equation d dx gamma d phi dx plus s equal to 0, we integrate it over each of the control volumes. Okay, so we divide our domain into a number of control volumes like this, depending on our problem. Say one control volume. Let us take this control volume, which I have shown by a dark line. This is one control volume. It has some arbitrary shape. It has how many? Five sides. Okay, pentagonal control volume, and is represented by a single grid point at its center. Typically, these grid points in common CFD languages are known as P. Okay, the point which we are doing calculation is known, and as we will see later for structured grids, the east eastern points are known as given by E and the western points are given by W. The top point, northern points are given by N and the southern points are given by S. This is the typical methodology. But easily one can also write this as I, and accordingly it will become I plus 1j, I minus 1j, things like that. But you cannot do this for this unstructured grid. Unstructured means this is very random, so you cannot how I is increasing in the X. There is no X and Y okay, for the grids. There the formulation has to be different for this type of problem, which we will see at the end of this course. But say, let this be the control volume. So you integrate this, whatever is your equation for this control volume, inter-control volume. So what does the integral look like? The integral over the control volume delta V is the volume of this control volume, okay? Not dV, delta V means it's a finite volume. d dx of gamma d phi dx dV, okay? So integral of the plus delta V s dV, okay? Integration of the second term also over the inter-control volume. Now by using divergence theorem, you just read about divergence theorem if you don't know. This volume integral can be converted to a surface integral. Okay, volume integral can be converted to a surface integral. We will see later for the general case. For a simple 1D case, the surface is just 2 points. Okay, east side and west side. Okay, so the volume integral can be written as I will come to the general case later. Gamma into A, which is the area of this east face, into d phi dx at the east side minus gamma d phi dx as the west side. Okay. And this integral, we can just assume that S is constant or some averages over the entire. Ultimately, if you have an average S which is given by S bar, so that into the volume will give you this integral term, right? So you have some value which is the average value into the volume is this integral. So S bar into delta V equal to 0. Okay. So the next step from here is where actually some approximation is needed in finite volume, and I will come to this part later. Okay, so just remember up to this point, this integral formula. Okay, this is the main, and it has certain advantages as we will discuss in a minute. So what are the main steps of the finite volume discretization? Again, the notes are already uploaded. You can go through the notes. And from now onward, we are also going to follow the Patankar book closely, as the old students know who have done CFD course. So the finite volume method, actually, Patankar himself had strongly contributed to this method. He has developed a lot of important scheme. He is a big person in this area of CFD. So he has discovered a lot of, or not developed or invented a lot of schemes, new schemes for finite volume, and that's why his methods are still very widely used. Like he has discovered the simpler and simple algorithm, all these algorithms, which we will study later. So one of the pioneers in this area. So his book also is, although it is very old book, 1980 book, means first version is 1980. Still, it has very deep insight if you go through that book. So main steps for finite volume discretization is that, again, divide the entire domain into a number of finite size subdomains, which we call as control volumes. We have already discussed. Each subdomain is represented by a grid point. So each subdomain is represented by a grid point, and integrate the governing differential equation over each subdomain. For each country, we have to integrate the governing differential equation like this. Okay. So from here to the next step, we have to change the volume integral to a surface integral using the divergence theorem, and then we have to assume something which is known as a profile assumption. This may not be clear to you right now. We will go through some examples today. So we have to assume. So see, when we are describing this variation, we only value at this point P, E, and W. Okay, which are at the center of this control values. Each of this blue box is a control value. Okay, so for example, this box corresponding to P is the control volume for P. Okay, we can call this as control volume P, and the grid point is the point at the center P, and the east face is face between this control volume P and the next control volume is called as the east face. Small, these are standard notation, and the phase between the control volume P and the left side, which is known as y, is given by small w, which is the west face of the control volume. It's a 1D problem, so you only have the east face and west face. So you only have values at this W, P, and E, capital W, capital P, and E. So to find any flux at the interfaces, you have to assume some profile. Okay, either you can assume that the temperature or phi in this case varies linearly between P and E, and you can calculate the values, or you can assume that they are just constant in each control volume, and you can calculate the value, or you can assume quadratic or cubic or some other profile. Otherwise, you cannot calculate. Okay, so this point will be more clear with examples. But for the sake of writing the steps, I have written it here. Consider a profile assumption for the dependent variable for evaluating the integral to express the results in terms of algebraic quantities. So ultimately, we want to get algebraic quantities at the grid points. Okay. To do this, we need variation of dependent variable as a function of independent variable. Means how the phi varies with x. This we need. We don't know this obviously because that is part of the solution. So we have to assume this, that phi is varying with x in this manner, like linear manner or some. So you can ask later on, but what happens if we assume wrong? So because we are assuming we do not know the solution. So what will happen? There can be multiple solutions or different assumptions, but at the limit, if you keep on increasing the number of control volumes and reduce the size of the control, all the solutions will converge to the correct solution, exact solution, means exact solution of the governing equation. Okay. So please note that for finite volume method, subdomains can be of arbitrary shape. Okay. As compared to finite difference method, where the subdomains cannot be of arbitrary shape, it has to be regular in shape. Otherwise, you cannot use Taylor series there. And any complex shape can be tackled relatively easily, unlike finite difference method, as we have discussed here. Okay. Again, I'm tapping the wrong button. So for finite volume, I could have just fitted some arbitrary triangular control volumes at the edges of this. But for finite difference, I have to go with some more complicated formulation, okay, to tackle the irregular boundary. So complex geometries are tackled relatively easily, unlike finite difference method. Okay. Let us go to a standard example so that you know what we mean by converting the integral into difference, like volume integral into surface integral and things like that. Let us take a break and then we will
Excuse me, sir.
jump to this. Okay. Yes, please tell me.
Sir, basically we are integrating the differential equation over individual control volume, right? And finding
Correct.
a single value, that is the grid point value, right?
Directly you cannot find, but please tell me your question first, then I will answer. Yeah.
Means we are integrating the conservation equation, then the final solution is a single value, right? The grid point value.
Correct. So
For the
what is
given
your question?
control volume, and yeah, that is the question, sir. Means question I'm confirming myself, that means it's finally we're finding a grid point value for the entire control volume, right?
Yes. The
Okay,
grid point value, which is representing the entire control volume. I will just clarify this, but it is better to clarify after going to the example. Okay, but still I will just clarify quickly here. So you are integrating over this control volume and you are getting some equation. Okay, that equation directly cannot give you the value at this grid point of the center of the control volume. Okay, it's just an equation which has the value at the grid point, but it also has neighboring grid point values. Okay, similar to finite difference equation, like the example that I have given in the exam to you. Okay, so it also has neighboring grid point values. So ultimately, you will again get a set of equations and set of which you have to solve to get these unknown values. These unknowns are all the and 10 unknowns. Okay, you have to solve by matrix inversion or any of the methods that we discuss later on to get these unknown values. So each of the unknown values represents its control volume. So it is actually at the center point, but you don't have any other known value at the in the control volume, like I have shown in the example here. Like what I have shown here in this example is that, say, this point here, okay, this point has a value of 1, this has a 0.5, and this has 0, for example. So everywhere, so actually the liquid fraction is not, like, the liquid is not obviously 0.5 at every location, right? This variable here, there is no liquid. It is so here there is defined liquid, or sorry, outside there is a different liquid, inside there is a different liquid. So here the liquid is different, here the liquid is different. Okay, you cannot capture that. Only thing you know is that for this control, the fraction of this red liquid is 0.5. Okay. Beyond that you don't know. So it is represented by a single point, and at the single point the value is 0.5. Okay. If it is a temperature, similarly for temperature you can, although TechPlot will show you interpolated results, it might be possible to show non-interpolated result also, right?
So means my doubt was that a single control volume can also have many points. So basically we are finding for a single point, grid point, how is it?
Single control volume does not have many points. That is the point. Means it is like a pixel. So now you can see here. Okay. This is our temp. This is the. Can you see the screen? This is from an actual example that we are solving. Okay. Each of the square is a control volume. Okay. Square control volume, regular control volume. Each is represented by the point at its center. Okay. So when you are calculating the temperature, you are getting the value of temperature at the center points of each of the square. Okay. You are getting the value of the temperature at the center point of each of the square. So what is happening is that, let me just a second. Okay. Okay, so each of these is at a, so now if you say, but I know the temperature at the center, it is like, say, something 3, for this point it is say 369 point something. Okay, what is the temperature at near the face or anywhere, any other place from the center? Okay, that you cannot resolve. Okay, so what we have plotted, the entire volume has the same temperature as the center point temperature. If you want to resolve it, you cannot do it. Okay, you may interpolate it. Means you know that temperature here is 370 and here it is 371 for the next. So if you assume a linear interpolation, you can then see the variation from here from 370 to 371 in a linear fashion. That you are interpolating, but your solution is not giving that. Your solution is giving that for the entire control volume, the temperature is a single temperature, 370, and for the next it is a single temperature. So it is like pixels. So this is like the minimum resolution that you are getting. As you can see here, each of the control volumes has a single temperature based on this that you are getting. Correct. So when we plot the results, we actually interpolate so that it looks like a smooth solution. But this is the real solution that you are getting. Each control volume has a single temperature. All the variables are single variables. Each control volume has a single velocity, single temperature. Okay. So it is at the center, but you cannot say what will be the temperature value at, say, 80% distance, or say 10% distance from the boundary. Okay, because you do not have a separate value there. No solution is there. Okay, so either you can say that this is equal to the center temperature 370, or you have to do some linear interpolation to find out the temperature based on the neighboring. So when plotting, we do linear interpolation like this. So instead of this pixel, you nice smoother plots like this. Okay, you get nice smooth plots like this. But this is just based on interpolation. This is not part of the solution. Okay, solution was a single temperature for each cell. Okay, so this interpolation is done calculating based on the neighboring values also. I just explained this so that others are also clear. Is it clear to everyone? What is the difference between control volume and grid point?
Yes, sir. Yes, sir. Thank you.
Okay. Let us take a brief break, 5 minutes, then I will join. Hello, can you hear me? My internet connection got dropped off. Can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So we will start. Okay. So suddenly my internet connection got dropped off. Let me share my screen again. Okay. So let us start the discussion. So steady state convection. So let us take the example of a steady state convection diffusion equation with no source term. Okay. So steady state means the first term is also 0, del t of rho phi, and source term is. Can you see the screen? Please confirm, one of you.
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
thank you. So source term is also 0. We are taking this to be 0. These are easy to handle, not difficult. Okay. So say this is the format, del dot rho u phi equal to del dot gamma del phi. Okay. So for a single control volume, we want to integrate over that control volume, right? We want to integrate over that control volume. I will keep this figure also open here on this side. So the P is the control volume, okay, and P represents its center point also. What is happening here? Reflexes are not good to do. So for any of this control volume, for this representative control volume, you integrate over the control volume del dot rho u phi minus gamma del phi, just taking that term to the left hand side. Okay, dV equal to 0. So this term rho u phi minus gamma gradient of phi, this is known as flux. Okay, so it's a combination of the convective flux and the conductive flux, diffusive flux. So you have the total flux, which is denoted by J. Okay, it's direction dependent, so bar is there because it's as U component. So the equation is del dot J dV equal to 0. Okay, for this case, we could have written separately also each of these, just to simplify and show you. So del dot J dV equal to 0 for the control volume. Okay, over the entire control volume. So what does this divergence theorem say? Physically is that any change that is occurring within the control volume is equal to the flux that is coming from the surface. Say you have some energy change that is occurring in this control volume. Okay, it should be equal to what is the how much energy is coming from the sides of this control volume. Okay, so this integral of this flux over the control volume, okay, which represents physically the change that is occurring over the entire control volume in the entire volume, okay, should be equal to whether any extra flux has come in or has gone out from the control volume surface. Okay, so this can be written as control surface J dot n ds, where n is the normal to the control surface. Okay, so say if you have a very arbitrary surface, at each small location you have to find what is J dot n ds. For this type of surface, you have 5 faces, right? So for each face, you can find out what is the value of J, means what is the value of flux, and the normal direction for each face is known. So from that we can calculate what is J dot n ds over the entire surface. So ultimate aim is that we are converting this change in the volume to some change that is occurring, to some quantity that is present at the surface. Okay, so this is for the entire surface control. So for the entire control surface, what is the flux along the normal direction of the surface? Okay, so if say velocity is not normal, so we have to take the normal component of velocity and then account for the flux. Okay, So while solving the problem, you will see that this is not difficult. Here it may seem some confusion may be there. You read about this, but the physical significance is this: that if certain flux comes from the boundary, the net total of the flux should be equal to the net change that is occurring in the volume. Okay, so because of conservation. So we have converted this kind of volume into a surface integral. Okay, and the surface integral is easy to calculate. Okay. So now let the grid point is at the center of the control volume, which is not always true, but it is the most common case. Okay, at the center of control volume, generally it is taken like this, but it need not be the case. For example, in some cases for boundary control volumes, we have the grid point at the edge of the control volume, not at the center. So now to calculate this flux across this control surface, say any of the surface, say take this surface, okay, left hand surface of this control volume. To calculate the flux here, what is flux? Flux means, remember what is flux? Rho u into phi at this point and gamma gradient of phi. Okay, to calculate this flux at this point, you need to know the values here, but you don't know the values here, right? You only know the values at the grid points. So it has to be represented in terms of the grid point values only. Grid point means it may be only these two grid points, or it may be a combination of all the grid points, but somehow it has to be represented by the grid point values, because you don't know the phase values. You cannot directly calculate across the phase. So to do this, you have to assume some kind of variation of this variable phi. How it is varying between each grid point. Say from this grid point to this grid point, it is linearly varying. From this grid point to this grid point, it is linearly varying. From this to this, it is linearly varying. So you have to assume some variation from one grid point to the other between the two grid points. Okay, this is an assumption. This is like no hard and fast solution is there. We don't know the solution even. We are just assuming some variation, like linear variation or some other variation. So we need to assume how phi varies from one grid point to another grid point. It can be linear, quadratic, constant. Okay, this is known as profile assumption. This assumption of taking some variation between two grid points without knowing the actual solution is known as profile assumption. We are assuming the profile of the variable phi. Okay, how it is varying without knowing the solution. Okay. So it means that the profile assumption can be very wrong also, and many cases it can be right. So multiple right solutions can be there. Ultimately, all the right solutions will give the correct result if the grid resolution is sufficiently fine enough, and so the fluxes will be calculated correctly. Okay. With suitable profile assumption, the flux can be written and integrated over the control surface to give algebraic equation in terms of phi at discrete points. Okay, so we'll see this example right now, how this can get converted to algebraic equation in terms of phi at each of the grid points. One important advantage of finite volume method is that this finite volume based discretization, because you are doing it by integrating the governing equation over the control volume, it satisfies the conservation of each of these parameters, like the conservation of energy, or like if you are using the governing differential equation for energy, conservation of energy or conservation of momentum over the entire control volume. Okay, and as a consequence, it satisfies the governing equation. It satisfies the conservation of properties over the entire domain. Okay, this is not trivial. Means for other cases, this may not be the case. For example, for finite difference method, your governing equations are only valid at the points, grid points. Okay, so these are differential equations. When you use differential equations, the conservation is still satisfied, because governing differential equation is based on conservation of properties. But the conservation of properties are satisfied at infinitesimal size, or at a point location. Okay, but the finite volume method, the way you are discretizing, it leads to satisfying the conservation over the entire control volumes. Okay, so inherently the properties are conserved, like total energy in the domain is conserved. But for finite difference, although you may get some solution, you have to check whether your solution is giving, means the energy is not changing over the entire domain with time. Things like that has to be checked. Okay, this is a very important property and difference between finite volume and finite difference. So why is this case? I have written a differential form of governing equation satisfies the principle of conservation. So differential form also satisfies the principle of conservation, but it satisfies over a single point, okay, point location, because it is in differential form. But the integral form of the conservation equation satisfies it over the volume, and we are taking the differential form and converting it to the integral form, okay, in some way. Now we will take a simple example. Means we are taking some examples, but we are not going through it. Means we are just getting stuck at some point, just to show you some of the factors that are involved in derivation. But now let us take a full example, okay, to see what it means, what this profile assumption, converting the volume integral to surface integral, all these things means. Okay. So for this again, let us go back to our 1D steady state heat conduction with heat source. So primarily this will be our first equation, and this is a representative equation. Although we are using it for heat conduction, this represents any of the equations of this form where you have a diffusive term. It can be, say, diffusivity of species or diffusion of momentum, means for example viscosity, okay, and some source term is there. It can be heat generation or some chemical reaction which is generating some chemical species, hydrogen and oxygen combining to form H2O. So this can be a equation for concentration of H2O, similar to that. So this is just the representative equation for our case, and in the next few sections we will just take this equation and go ahead. Gradually we will add more term like unsteady term, then convective term to this, to see how it needs to be solved. Again, the old students already know, who have done CFD course with me, because it is almost syllabus is similar at this point. Okay. So this is our governing differential equation for one this steady state heat conduction, and let us have a domain, because it's a 1D problem. Our domain is say from 1 to 8, and we are dividing, so it is similar to your exam problem, and we are dividing into 6 1 2 3 4 5 6 control volumes. Okay, so this one control volume goes from 1 to this point, second one from, so these black lines are the boundary of the control volume. It's a 1D control volume, so the control volumes are like lines. Okay, it does not have actually it does not have any volume. It's just the line. It only has length. So from this point to this point is one control volume. This to this one control. So you have 6 control volumes: 1, 2, 3, 4, 5, 6, and then you have 2 boundary control volumes of 0. Consider them as control volumes, but you have 2 boundary points, heat points, which has the values known or like part of the boundary condition. Okay, 6 internal control volumes are there. Let us take a typical grid point, say any of the grid points, say this grid point 5, okay, and the control volume 5. So this control volume 5 is, it may not be at the center, but for our simple calculations we will assume that it is at the center. Okay, centroid here is the center simply. So this typically this is represented in this way. Okay, the control volume that we are considering is represented by the variable P. Okay, this is the standard notation in CFD. Some books also use Ij like this, I plus 1, I minus 1. We will use the standard Pattankar notation. So this is P. The next grid point on the right hand side, which is the east side, is given by capital E. So all the grid points are denoted by capital letters. Okay, and the next grid point on the left side, which is the west side, is denoted by capital W. Okay, so I have drawn this section from going from this point 4 to point 6. Okay, so one full control volume and 2 half control volumes are shown here. Okay, one full control volume, which is this corresponding to 0.5, is given by this blue lines. Extent is given by the blue lines. Okay, so the length of the control volume is delta x. So from here to here it is delta x. Okay, left side, left face of the control volume is denoted by small w. Okay, west face, and the right face is denoted by small e, east face. This is the standard notation. So your control volume goes from west face to east face, and at the center you have the grid point capital P. Next control volume has capital W on the left side and capital E on the right side as the grid points. Okay, so the distances between these grid points are represented by delta XW and delta XC. So remember that although we are showing here as equal division of the control volume, finite volume formulation can be done in a very generalized way. So each of the control volume can have different lengths depending on our problem. So we need to say calculate the flux near the boundary. So here I will have very fine grid points, or say it is like a aerofoil structure. Near the aerofoil surface you need very fine grid points. Okay, but far away from the aerofoil structure you don't need to capture the flow separation, other things. Far away there is not much variation. You take coarse grid points. So similarly, our formulation can have fine or coarse grid points. So each of the, not grid points, sorry, control volumes. So each of the control volume can have different lengths. As a result, the distance also can be different. Okay. So let us call this distance as delta xw and this is delta xc. For our simple case, these two are equal, but in general they can be different. Okay. So integrating our governing equation, so we have to integrate the governing equation, right, over the control volume. That is what we have described. Control volume goes from small w to small e. So going from small w to small e, d dx of k dt dx, because we are integrating in the x direction. Volume is in the x direction in this case. It's only a single line. If it was 2D, it would be dx dy. And the source term also integrating it from west to east along the x direction, s dx. Okay. So this volume integral can be now written as a surface integral. So at here the surface is actually just 2 points, east point and west point. So k dt dx at east minus k dt dx at west. Okay. So the change in whatever happening in this volume is equal to the change of flux or whatever comes in from the east and west phase. Okay. So k dt dx east minus k dt dx west plus assuming constant source term over the control volume s into the length of the control volume delta x. Okay, s into delta x. xc minus xw is delta x. So s into delta x. Okay, assuming constant source term. K dt dx east minus k dt dx west plus s delta x. Any questions up to this point? Okay, we'll continue. Okay. I have to end the class a little quickly today. I have to have some other work. So we need so now calculating this k dt dx at east and west poses the problem because we don't know what is the value of k dt dx at east. Okay, basically we don't know what is the value of dt dx at east and dt dx at west. So what to be done? What is to be done in that case? Okay, so we have to assume that the variable T, temperature, varies between point P and E in some manner. Okay, it can be linear manner, it can be quadratic manner, but in some manner it is varying. And if we assume that variation, say it is linearly varying like this, then you can calculate dt dx at this point based on that linear variation. But it can be quadratic also. Then the dt dx will have a different value because your slope of the line is different at this point. So depending on the profile assumption, the slope can be different for each case. Okay, flux also can be different. This is a tricky concept to understand. You can say that, but then how is it that rejoin me? Prabhat is there or still unable to rejoin? Is calling. Okay. So we will come into this. What can be done? Like what are the typical assumptions that can be tolerated or that can be acceptable? Okay, but we need some assumption. Okay, let us start with the profile assumption. We will just finish this class with this profile assumption and continue in the next class and the other cases. Okay. So let us assume the simplest case, like what I was saying to you when I was showing this domain, that each of these control volumes is represented by a single value at its grid point. Okay, each of the control volumes has a constant value equal to the grid point value. This point has a constant value equal to the grid point value. Okay, so for this control volume P, the value is constant. It is equal to the grid point value. So this value is Tp. Okay, I should write here it is equal to Tp, temperature at point P. Similarly, this for the central control volume on the left hand side, the value of temperature is TW. And for the entire control volume on the east side, right hand side, the temperature is TE, T capital E, whatever is the grid point temperature. Okay. So this is the simplest profile assumption. We are assuming that temperature is constant within each control volume. Is this acceptable? Can we calculate these terms based on this assumption?
Yes, sir. So large.
How will we calculate the dt dx at the interface west and east? Not possible. Okay, it's not continuous. The temperature is not continuous at not, you cannot calculate the derivative also. Okay, at the interface, it's like direct jump is there. Derivative is infinite. So this assumption is not acceptable. Okay, this assumption that the control volume means our profile assumption that the variation within the control volume is linear, not linear, sorry, constant, is not acceptable for resolving this derivative terms. Okay, k dt dx east and west. We cannot calculate dt dx at the interfaces of the control volume based on this. Okay, so we cannot use this. Let us take another simple. Next, you can say that okay, we will assume that they are connected like this within the control volumes. Okay, so at point P we have a certain value Tp, and the variation within the control volume is linear. Okay, it goes like this. Okay, at point W we have a certain value Tw, and it goes across like linear. So it changes within the control volume in a linear fashion, so that at the boundary points, like at the faces, not boundary point, at the faces, they are equal. The temperatures are equal. Okay, so at least there is continuity of the temperatures. There is no jump in temperature. Jump in temperature is not possible physically because there is no resistance here, right? So at least the temperature is there is continuous. Okay, there is no jump in temperature. So at this faces, k dt dx at east and west. Any answers? What will happen if I want to calculate k dt dx at west point here? How will you calculate this k dt dx at west based on the grid point values or for this linear assumption? If I ask you what is the slope of temperature, at what is
So
the
it is
answer?
still discontinuous.
Slope is discontinuous, right? Slope is still discontinuous. Temperature is continuous, slope is discontinuous. Slope is changing at the grid point. So dt dx is not continuous at the grid point. dt dx is not continuous. This is a big problem because if k is constant, k dt dx should be same on both sides of the control volume because whatever heat comes from this side has to go to the other side. So k dt dx has to be equal at this interface, right? We cannot have two separate k dt dx at the interface. So this profile assumption is also not correct, means not acceptable. Correct? There is no correct solution, but not acceptable. Is it clear why is it not acceptable? Because the slopes are different. So when you are calculating for this control volume P, you will be calculating based on this profile assumption. Correct? So when you are calculating for the control volume P, dt dx east minus k dt dx west, you will just take this profile assumption and you will get some value of dt dx at this point, okay, based on this profile assumption. Then when you are moving on to the next point, say this point, this control volume E, you are again doing the integration over this control volume and calculating this flux here and flux here. Now the flux that you will calculate here will be based on this slope, okay. So for this east control volume, your flux is given by this slope. For this P control volume, the flux is given by this slope. So the flux is not equal at the faces, but flux needs to be equal at the faces, right? So it means that this is also not acceptable. K dt dx is not continuous at the interface. As the heat flux is not equal on both sides of the interface, this assumption is not acceptable. Okay. Next, we will assume another type of profile assumption, piecewise linear between each grid point. Okay. The temperature can change, means there can be change in slope, but the temperature is continuous from one control volume to the another control volume, like a line. So between Tp and Te, it is linear variation. Between Tw and Tp, it is linear variation. But if you consider the control volume going from small w to small e, the temperature goes like this and again this. So which is unphysical, but remember, this is only for discretization. The final solution is independent of this, whatever is the profile assumption. Our main aim is to resolve the fluxes at the interface. Okay, so based on the grid point values. So with this profile assumption, now dTdx can be calculated. Okay, because what will happen? dTdx you previously also you could calculate, but now the dTdx you will calculate for this control volume P. When you are calculating for the control volume P, you will calculate minus k dt dx e at this point based on this slope. And when you are going to the next iteration, when you are calculating for the control volume E, then you are calculating the flux here again based on the same slope. So ultimately your flux is equal on both sides, okay, for both the control volume. So it is physically consistent. Heat flux is continuous and profile assumption is valid. Okay. So based on this profile assumption, you can write this. This is the same equation that we had previously written. K dt dx east minus K dt dx west plus S into delta x. Okay. So now we can, as we can write, I will just make it smaller. That this diagram is present. So interface value of conductivity. Let us right now don't bother with what is the value of conductivity at the interface. Let us assume that we know this conductivity at the interface. So K at small e, okay, into dt dx at small e. What is dt dx at e? Te minus Tp into this distance between E and P and E. Okay, this is delta xc. If you remember, we have shown this as delta xc. Okay, P and D. These are standard notation. Let us go back to it. Te minus Tp by delta x. Similarly, for this west phase, again let us assume that we know the conductivity Kw. So this is given by Tp minus Tw by delta xw, okay, and plus S into delta x. Delta x is the length of the control volume. Delta x need not be equal to delta xc and delta xw. But if you divide the domain into equal size control volumes, all these three terms will be equal. Okay. But for a general solution, this need not be equal. So this Ke and Kw at the interface is also not known. They are also represented at the grid points. They have to be calculated by some averaging at the interface. Okay, that we will discuss later how the averaging needs to be done. Either you can do linear interpolation or something, but that has to be calculated based on averaging. We will see later that linear interpolation is not good. You have to take harmonic mean. Okay, but that is for future discussion. So once you write this, now you just take the accumulate the all the coefficients of corresponding to each of the temperature value. You have three temperature value Tp, Ta and Tw. Okay, if you accumulate these coefficients, you get an equation of this form: Ke by delta Xc plus Kw by delta Xw Tp is equal to Ke by delta Xc Te plus Kw by delta Xw Tw plus S into delta X. That X is missing. It has got cut off during scanning. Okay, S into delta X, which can be written in the standard form, standard notation. APTP is equal to AET plus AWTW plus B. Okay, this standard notation for this finite volume formulation gives for the control volume P the variable Tp as a dependent variable in terms of its neighboring grid point variables Te and Tw in this case. If you have a 2D problem, we will have two more neighboring grid points on the top and bottom. Okay, like this, north and south. And the coefficients which are known values. AP is equal to this and the conductivity is known, delta Xc are known from your mesh generation, conductivity is known from interpolation. AE and AW are also known. So the coefficients, these are known as coefficients of this discretized equation. AP, AE and AW, all these are known values. B also is known because source term is known and delta X is known. So B is also known value. B is all the source terms are put together in B. Okay. So So this is the standard notation for finite volume algorithm where you write APTP. So where P is the concerned grid point or control volume in terms of its neighboring grid points, summation of A and B, T and B. If we have 10 neighboring grid points, we'll have summation of all the 10 neighboring grid points. Here we have 2 neighboring grid points, east and west, so we have summation over these 2 grid points plus any other source term B. Okay. This is the standard notation where grid point variable value expressed in terms of its neighboring values. We will continue this discussion further in the next class. Let me go back to this general point. Okay. So if this was the case, you have 5 faces, right? How many neighboring grid points does this have? All these faces are considered to be neighbors. Okay. So 1, 2, not the corner ones. 1, 2, 3, 4, 5. So 5 neighboring grid points are there. So your equation will be APTP is equal to summation of, say, this is A1, A1 T1, A2 T2, A3 T, A4 T4, A5 T5. So all the neighboring grid points will come into picture in the formulation for this type of unstructured grid. Whatever is the number of neighboring points will come into picture. We'll continue this discussion further. It is there on Patankar also. Maybe not in so much detail, but Patankar is a very concise and short book, but to the point. So you can also go through that. Okay, but it has a lot of deep insights. I will take attendance and then we will finish the class. Any questions? I am slight hurry today. Slight hurry. If you have questions, ask me in the next class. I have to go for a meeting now. So we'll just quickly take the attendance.